Chapter 5, Probability Distributions. Key concept: this section introduces the concept of a random variable and the concept of a probability distribution. We illustrate how a probability histogram is a graph that visually depicts a probability distribution. We show how to find the important parameters of mean, standard deviation, and variance for a probability distribution. Most importantly, we describe how to determine whether the outcomes are significant, significantly low, or significantly high. Basic concepts of probability distributions. The random variable. A random variable is a variable, typically represented by x, that has a single numerical value. Determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value of the random variable. And we often express it as a graph or a formula, sometimes a table. Discrete random variables are random variables that take on a finite or countable number of values. Countable means there's infinitely many. Finite means a finite number. Continuous random variables have infinitely many variables, and they're not countable in the sense that you cannot put them into one-to-one correspondence with the natural numbers. Every probability distribution must satisfy each of the following. There is a numerical random variable x, and its number values are associated with corresponding probabilities. The sum of all the probabilities of the random variables is 1. Possibly due to numerical errors, numbers close to 1, plus or minus. And the probability of each random variable has to be a number between 0 and 1, possibly 0, possibly 1. Consider the coin toss. Our random variable will be the number of heads when 2 coins are tossed. So the possibilities are heads, heads. Sample space consists of heads, 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 tails, tails, heads, tails, tails. So the probability of getting no heads would be 1 in 4, because you could flip the coin and get tails, and then flip the coin again and get tails. So 1 out of 4 corresponds to 0 heads. But there are 2 times that you could get exactly 1 head. If you flip, get a head and then a tails, or get a tail and then a head. That's 2 out of 4. Corresponds to the 0.50 here. Or you could flip the coin and get heads both times, which corresponds to this event in the sample space and this probability in our table of 0.25. The variable x is a numerical random value variable, and it's discrete because it can only take on values between 0, 1, and 2, numbers that you could count, and a finite number of numbers. So the sum of the probabilities from our table previously, we had 0.25, 0.50, and then 0.25, which do indeed sum up to 1. Remember that sigma, capital sigma notation means sum, in addition. And each of these probabilities is between 0 and 1. This is a histogram for our probability distribution that we constructed above. Notice that for 0 heads, the bar goes up to 0.25 because the probability of getting 0 heads from 2 coin tosses is 0.25, 1 out of 4. The probability of getting 1 head, getting a coin twice, is 50%, 1/2, 0.50. And the probability of flipping heads twice would be 1 in 4. So this bar here goes to 0.25. So probability distributions can also come in the form of a formula. And we'll see what this formula is saying here in a minute. So notice that if we were to take 0 and plug it into this formula, the probability of 0 given this formula is 1 over 2 times 2 minus 0 factorial times 0 factorial. Recall 0 factorial is 1. We have 1 over 2 times 2 factorial times 1, which is 1 over 2 times 2 times 1, which is 1/4. P of 1, plugging 1 in for x, we have 1 over 2 times 2 minus 1 factorial times 1 factorial. 2 minus 1 is 1. We have 1 over 2 times 1, which is 1/2. No coincidence, P of 1 is equal to 0.5. And you can verify plugging 2 into this formula would get you 0.25. So this formula encapsulates our probability distribution above. Here's an example of a table that is not a probability distribution. We have, this is a list describing various things that hiring managers find to be mistakes during the hiring process. Inappropriate attire, being late, lack of eye contact, checking their phone or texting. And here are the probabilities that a given hiring manager will find these behaviors to be objectionable. But notice the sum of the probabilities is greater than 1. So this is not a probability distribution. And recall that with a probability distribution, we have a description of a population instead of a sample. The values of mean, standard deviation, and variance are parameters and not statistics. We can find these parameters with the following formulas. Mean of a probability distribution is the sum of the x values times their respective probabilities. And variance requires us to take the sum of the x values minus the mean, square them, and then multiply by the probability distribution. And then a handier form for calculations be to compute each x times its respective probability. X squared. And then multiply that times, or subtract from that, mean squared. This way you're only computing squared one time. And standard deviation is simply the square root of the variance. Expected value, the expected value of a discrete random variable x is denoted by capital E, and it is the mean value of the outcomes. So the expected value is the mean, and we can find it with our formula for the mean. Here's our table for tossing a coin 2 times, our probability distribution. Let's compute mean, variance, and standard deviation. So recall our probabilities. The probability of getting 0 heads from 2 coin flips was 0.25. The probability of 1 head was 0.50, and the probability of 2 heads 0.25. The total sum of those probabilities is 1, as you can verify by adding up all those entries. So the meaning of this formula here is to take each x, multiply it to its corresponding probability, and then add up all of those products. So the first x, the first random variable, 0. Probability of that random variable is 0.25. Get a value of 0 for that product. The next random variable, 1, has a probability of 0.50. So multiply it to its probability and you get 0.50. The next discrete random variable is 2. And those are the only, here we have a finite number of discrete random variables. So 2 times its probability of 0.25 be 0.50. Sum all of these up, get 0 plus 0.5 plus 0.5, which is 1. That is mean. To compute the products we need for the variance, so notice this part of the formula for the variance, we get a table. This column here will record those values. So we need the value, which is 0, minus the mean, 0 minus 1, square that, times the probability of 0 times 0.25. So 0 minus 1 is 1. 1 squared is 1. 1 times 0.25, we'll get 0.25. Then for the next entry, when x is 1, 1 minus the mean is 1 minus 1 squared times 0.5. Which is 0 times 0.5, which is 0. And then for x equal to 2, we have 2 minus 1 squared times 0.25, which is 1 squared times 0.25, which is 0.25. Sum all of those up to get 0.50. So the variance is 0.50. The standard deviation is simply the square root of the variance. So since variance is 0.5, write that down. Standard deviation is the square root of the variance. And the variance we computed to be, in this case, 0.5. So we get standard deviation of square root of 0.5, or 0.7. The interpretation is that the mean number of heads, or the number of heads that we expect, is 1 head for any two sequential coin tosses. And the variance is 0.50 heads squared. Standard deviation is 0.7 heads. If we were to conduct this experiment a large number of times, we would expect to get 1 head the majority of the time. So here's an example. When conducting research on color blindness in males, a researcher forms random groups with 5 males in each group. The random variable X is the number of males who have a form of color blindness. So to determine if this is a probability distribution, and if so, find its mean and standard deviation. Okay. So go to your StatCrunch. And in one column, input the X values. Those are your discrete random variables. And then in the next column, put in their associated probabilities. Once you have that, go to Stat, Calculators, Custom. Select variable 1 for values in, and then select variable 2 for the weights. The custom calculator knows to set up mean and the standard deviation, just like we were doing in the previous example. And then hit compute. and you can read off mean here and your standard deviation here. So the mean 0.397 and the standard deviation is next topic, identifying significant results with the range rule of thumb. The range rule of thumb for identifying significant values is it is a significantly low value if it's less than the mean minus 2 times sigma, and it's significantly high if it's greater than the mean plus 2 times the standard deviation. So we found that when tossing 2 coins, the mean was 1 head and the standard deviation was 0.7 heads. So use those results in the range rule of thumb to determine whether 2 heads is a significantly high number of heads. Well, we take 2 heads is greater than mean, which is 1 head. So we want to know what mu plus 2 times the standard deviation is. That's going to be 1 plus 2 times 0.7, which is 1 plus 1.4, which is 2.4. So 2 heads is less than 2.4 heads. So getting 2 heads out of 2 coin tosses is not significantly high. It would be significantly high if 2 heads was greater than plus 2 times sigma. So it's not possible in this case to get a significantly high number of heads. So significantly high number of successes, X successes among N trials is significantly high if the probability of X or more is 0.05 or smaller. If the probability of X or more is less than or equal to 0.05, it's significantly high. And similarly, it's considered significantly low if the probability of X or fewer is less than or equal to 0.05. So if under a given assumption the probability of a particular outcome is very small and the outcome occurs significantly less than or significantly greater than what we expect with that assumption, then we conclude that the assumption is probably not correct. So this is going to lead into the concept of hypothesis testing, which we'll discuss later in the course. For hypothesis testing. This table describes the results of roadworthiness tests of Ford Focus cars that are 3 years old. Random variable represents the number of cars that failed among 6 that were tested for roadworthiness. Is the probability of getting 3 or more cars that fail among 6 cars tested significant, determined by the cutoff value of 0.05. So the probability of 3 or more cars failed here. So that includes 3. It's going to be this probability of 0.041 plus this probability of 0.005 plus the probabilities for 5 and 6, which were so small or exactly 0. They are 0. Probability of just 3 cars would be 0.041, but the probability of 3 or more means add up all of these probabilities from 3 onward. So then we get 0.046, which is less than or equal to the cutoff of 0.05. Well, it's less than. Okay. So the probability of 3 or more cars failed is less than 0.05. So this is significant. Significantly low. The expected value of a random variable is equal to the mean. So we can therefore find the expected value by computing, the mean. In formula terms, the expected value of x, brackets indicate this is a random variable, is the sum of x times the probabilities of each x. So here's a gambling example. Suppose you have $5 to place on a bet at a casino. And for roulette, if you bet, the bet you're going with is to bet on 7. For craps, you're going to bet on the pass line. We'll have the various odds down here. So for roulette, the probability of losing is 37 out of 38. Probability of winning is 1 out of 38. And there's a net gain of 175 for a $5 bet. So find the expected value. the expected value is going to be the sum of the net payoffs, the probability of the net payoffs for each. So the expected value of X is equal to, well, you have a net payoff of negative $5 if you lose. So the event of losing $5 has an associated probability of 37 out of 38. And then you add that to the event of gaining $175. So your net gain is the event of gaining $175 has an associated probability of 1 out of 38. You could think of it as a table. Put your net gain one column, well, you lose $5, and the probability of that gain is 37 out of 38. And the only other possibility is winning 175, and the probability of that is 38. This is your X, your first random discrete random variable, and your second. And this is the probability of that random variable. This is the probability of that random variable. This is P of X2. This is X2. Oh, excuse me, P of X1. This is X2, and this is P of X2. These are the amounts we get. Negative, well, let's verify here. Take 5 times 7 divided by 38. Negative 4.87. And add that to 75 times 1 divided by 38. That's 4.61. So 4.61 plus negative minus, or 4.87 is negative 0.26. Dollars, 6 cents about. So minus 26 cents is the expected outcome. Now the odds for craps will lose $5 251 out of 495 times, and you will gain $5 244 out of 495 times. So what would be the expected outcome here? Well, net gain of minus $5 has an associated probability of 251 out of 495, and a net gain of positive $5 has a probability of 244 out of 495. That's your first discrete random variable. That's your second. That's the probability associated with your first discrete random variable and the probability associated with your second. So the expected net gain, so E, not a sigma, is the sum of the products of each random variable, each possible outcome, times its corresponding probability. So we have negative $5 times 251 out of over 95 plus 5 times 200 over 195. Five times 251 divided by 495 negative $2.53. 5 times 244 divided by 495 is 2.46. So 2.46 plus negative 2.53 is negative 0.07 minus negative 7 cents. So you expect to lose less if you go with craps. So, and you expect to lose more if you go with the roulette. The payoff is higher, but you can expect to lose more money. So that's our interpretation here. The $5 roulette bet has an expected value of negative 26 cents. And the $5 craps bet has an expected value of negative 7 cents. So in the long run, you'll lose more money in the craps game, even though the payoff is potentially higher. Life insurance. Is it a gamble? So there is a 0.9984 probability that a randomly selected 28-year-old male lives through the year. A life insurance company charges $190 per year for insuring that male. If the male does not survive, the policy pays out $80,000 as a death benefit. So, from the perspective of the male, what would be the value of surviving the year? Well, if he survives the year, he loses $190. So minus 190. And that is his net gain. Now, what would be the value corresponding to not surviving the year? Well, it would be whatever the payout is, 80,000 minus 190. So $79,890. 110, excuse me. So, what is the expected value here? The expected value, well, we could come up with a chart of net gain and the probability. So there's a net gain loss negative $190, and that's 0.9984. That's the probability. It's very likely that that's going to be the outcome. The 99.84% chance that the male will survive and then be out $190. But you either live or die in a year. So the complement of that be does die, then he gains 79,810. Well, factors people he leaves the money to. So that would be a probability, the complement of this, 1 minus 0.9984, 0.0016. So the expected value is the sum of the net gains times their probabilities, negative 190 times 0.9984 plus 79,810 times 0.0016. $190 negative times 0.9984 plus 79,810 times 0.0016. The expected value is negative $62. Can the insurance company make a profit from such a policy? The answer would be yes, because they can expect on average that any given customer will pay them $62. The small fraction of their customers will die, and they'll have to pay out $80,000 to that customer. But on average, the company expects to make a profit of $62 on each 28-year-old male it insures for a year. That concludes this lecture.